components must reach the front so you can record it. So this fails since our purple thing does not reach the front. And if it doesn't reach the front, I call it an island, but that's... So basically, you have to have everything reaching the front. So if you make an array, a proper m by p, a three-dimensional proper array by gluing rectangular faces from back to front, when you grab it by the front face, everything holds together. And all the arrows, all the connectors, circle connectors are sticking out. Okay, so oh, finally got it right. All right, and so if you do that correctly, you can build a 3 by 3 proper array. You're really only going to count the dimensions of the preferred face. Now this is 3 by 3 by 3, but this can have as many columns, as many faces if you want to extend it backwards. And so here is, in fact, I'm going to let you look at the model. I only put the pink in. Pink's supposed to have the connector sticking out, but so it holds together. But this is the example, and notice we have all the colors reaching this front face, and all the little plugs, circles, connectors, I sometimes call them arrows because I originally represented them as arrows, are coming out of the front face. And so you can experiment with this example. What you'd have to do is, here it is. Now you're going to have to maybe use your imagination just a little bit, because I have plugged in, the blue wouldn't be plugged in, it would be loose, and the pink wouldn't be plugged in. But the idea is, here it is, here's this exact model where the case is built. And so now the idea is, once you get everything reaching the front, you can record it as, you can take the three-dimensional situation and take it down to counting two-dimensional situations, which is reducing it in size, just like we did before with the plane, got it to a column. So now we're going to go from 3 to 2, and so basically you take this face, any component, path connected component, you record as a letter, and if it has a circle and a connector extended outward, I just record it as a circle. And so what these are the states of the transition matrix, and so it's going to give you the size of the matrix I need. And so this is why I wanted to be able to count this, so a priori we knew how much memory to assign to the computer to construct the transition matrix. There's a 3-stage Maple program, and if it got really big, we needed to know whether we have to send this off to other computers and do injections and stuff. And so this is the other aspect of accounting these by generating functions and very combinatorially, and that's what I'm going to be focusing on. So you almost now, even if you didn't quite understand transition matrix, you can almost just say, look, take this model and go down to this picture. I'm going to count these. And I call these the letter representations of states. Okay? Now there's one trick. I have to mention that this thing is exactly the same as if I changed the A to an X. I'm just really counting the partition structure. The letter is just a label. So please don't get confused, and you'll see that when I do the reflections and stuff. That the letter might change, but I might say it's considered the same thing. All right. So, okay, so we're going to work with squares. Now, squares, the idea when this transition matrix, to simplify the computer time, I wanted to work with the symmetry and keep everything at a symmetry of a square face, basically the dihedral group, say it's counted once. So, all 8 of these, this is a hard picture to see, I can always give you a close-up of it later. All 8 of these are going to be considered the same thing in my count. So you basically have to deal with horizontal reflections, vertical reflections, and diagonals and rotations. All right. All right, now here's a nasty slide, but if you know Burnside's lemma, the upshot isn't too hard. I want to get a bunch of generating functions that I can put together to count what I'm calling the letter representations, giving me, I want to count a generated function that for any square will count how many of such configurations I can get like this. Now I'm describing the lower bound. To get the upper bound, I'm going to have to put on the circles. And when I say lower and upper bound, I mean for the basis of the transition matrix. All right. So I'm just going to describe the lower bound because the geometry is very interesting. And it's just a little bit, you have to just tweak it just a little bit to get the upper bound. And you understand the lower bound and the symmetry, the upper bound is just a variation. All right. Okay, so what we're going to need to do is the upshot is, you might want to remember, we're basically going to need to count horizontal. The hedral group, you have a horizontal reflection, a vertical reflection, a 180-degree rotation. Think of the symmetries of a square in the plane. A 90-degree rotation, and a diagonal reflection. So what we're going to really need in all this was a very naive count of how to do this if you didn't know Burnside's lemma. But what you're going to have to remember, H goes for horizontal, V for vertical, R for 180-degree rotation, N for 90-degree rotation, and I for like flip inversion. So the whole upshot is if you get the generating functions for H, V, your horizontal, your vertical, your 180, your two diagonal reflections, and your 90-degree rotation, you basically can get how many letter representations are. And that's really by Burnside's lemma. You're seeing what are fixed by these actions. So, and I should mention that Bn is the Bell number. Okay, so we know, I'm hoping in this group we might know what hopefully the Bell number is. It's just the base count. And it's the Bell number for n squared, by the way. I think I said that all the way at the beginning. All right, so now.
Like the other sequences you don't know, Hn.
Oh, I know them.
Oh, you know them all?
I know them all. Yes, I know them all. I'm going to describe now how to help us figure out H.
Oh, it's coming up.
They're coming up, yes. They're all coming up. We're going to describe.
So Bn is Bell number of n squared?
Yes, Bn is Bell number of n squared, yes. So I was told somewhat by the editor that we don't want to put n squared, as we see, Bn squared, it's all the way hidden up here, it's B sub n. He told me that didn't look good with n squared, get rid of it. So I said, since we're doing a square, we know it's an n times n, just say Bn. So yes, remember we're working in a square, so the n is the side of the square. Okay, now we're going to get to some nice looking slides. So I do know how to build these generating functions. And the key to this thing is you have to take your symmetry, and you have to basically take your underlying square, and you have to divide it into either halves or quarters depending on your symmetry. And the other trick is you basically, okay, so you fill it in halves and quarters. You fill out your top half or your little quarter. You use the symmetry to determine the rest. The only trick is you have to worry about whether there's any fixed rows or columns. So a lot of these generating functions have to be done with parity, even and odd. So I'm going to start with the easiest case. And we're going to do a horizontal, we're going to look at square letter arrangements that are fixed by what I mean by horizontal reflection. All right, so let's take this first sample. And I have to probably help us understand what I mean by horizontal reflection. Now here's the trick. I sometimes find that the graduate students always got this better than the professors. I tried to explain what a reflection was to them, the professors, and said, this is not right. It can't, but you have to do renaming. Okay, so let's suppose I gave you this arrangement of symbols. So I have a heart component, a club component, and a square component. Start with that. Reflect it over. This is my reflection line. Now, would I consider these two the same in my count? Yes, that's right, because I could always rename the component structures the same when I reflect. I have something going this way, something going this way, and that, and when I reflect, I get the same kind of component structure. So what you could take in your head, if you didn't like that, if you didn't see it immediately, is you could rename into heart goes to club, and square goes to the same, and if you get a renaming that gives you the same thing originally, then the component structure was the same. Yeah. It's the renaming they didn't like. It's not a strict, it's not a traditional sense of reflection. It's basically saying the partition subpartition structure is fixed under reflection. All right, so here's a test. Is this going to have horizontal symmetry? Yes, yes, because triangle and square could be renamed. Yeah, yeah, see, I told you, the students get this. The professors hated it because it wasn't traditional. Can't help it, but that's good. That's the key. That's what I'm going to be using. So that's like saying A and X interchange to mean the same thing. I just use simple